All right, what do we got? Modeling a gas. We have pressure is force over area. So pressure should be in pascals. What, newtons, square meters, right? Oh, this is moles. This is basic chemistry, right? The moles you've got is equal to the number of particles you've got over Avogadro's number, right? 6.022, right? This is the number of particles you've got. That's useful, right? And then, of course, remember also that N is also equal to mass over molar mass, right? This is Puvnert, right? Remember, temperature has to be kelvins, right? That's your ideal gas law constant, right? The gas constant. Volume has to be cubic meters. This has to be moles, and this has to be pascals, right? So be careful with that, right? It's going to be pascals times cubic meters has to equal moles times, what is it? It's joules per mole Kelvin. I think are the units for that, and then kelvins, right? Is that true? So the moles cancel, right? Kelvins cancel. Is a joule a pascal times a cubic meter? I think it is, because the pascal is a newton per square meter, and then times, there we go, newton meter. Yeah, it's a joule. So those are the units for that, right? And then this is Boltzmann's relationship, right? Is that the average kinetic energy, right? Which you could say that that's equal to 1/2 mvrms squared, right? Is equal to 3/2 Boltzmann's constant. So look that up. It's the one with the KB, right? We looked at it earlier, right? Times the temperature. Okay. This is interesting because the 1/2 sort of comes from the 1/2 mv squared. The 3 comes from there being 3 degrees of freedom for a monatomic gas. That is, it can move in the X, Y, and Z regions, right? And this changes. If it's a diatomic gas, golly, I want to say it's like 5 or something like that, because a diatomic gas can also rotate. It can rotate this way, and it can rotate about an axis coming straight out of the page, and it can rotate about an axis in the page, right? So it has 2 more degrees of freedom, and then I want to say, I don't know. Anyway, it's beyond. We're only going to do ideal gases, and so it'll be always 3. But this is cooler than this expression shows you, right? And then it turns out that Boltzmann's constant is just the gas constant divided by Avogadro's number, right? So you can also do it this way. It's up to you. I mean, I don't. Yeah. They're the same thing, right? Ultimately, you can put that in here. If you know the mass of the particle, you can figure out the velocities. And these velocities are tremendous, okay, because the particle mass is so small. I think it's like 400 meters per second for nitrogen at room temperature, something crazy like that. And this is the RMS, the root mean square, right? If you solve for V, it's the root of this is the square of the mean of the squares or something like that. Anyway. There you go. That's that section.